I'm going to show you how table partitions are one of the best kept secrets to scaling Postgres. They allow you to break up massive tables into smaller chunks, making your queries much more efficient and your data more manageable as it grows. Let's get into it. So here I have a table of people, over 10 million people to be exact. And each one has an employer. Now we all know FAANG companies are no longer cool, so everyone here works for Microsoft, Amazon, Nvidia, Google, OpenAI, or Supabase. What? It's a totally consistent list. It's all the Mangoes companies. But each person who works for one of these companies should only be able to see and modify data for their specific company. So imagine our application is making a bunch of requests to this database. So let's say they want to select all of the columns from the people table, but then are always filtering it down to where the employer is equal to one of those specific companies. So if we wanted to find our top salespeople for the quarter, we'd have our specific employer, and then maybe where the sales date, which is an imaginary column that doesn't actually exist in this table, but let's say the sales date is between 2023 and 2024. Again, this is a nonsense query, but just to demonstrate the point that every time our application is making a request to the database, it's specifying which employer it's querying on behalf of, because each one of those companies is in their own little sandbox environment within that table. This pattern is usually called a multi-tenant database, where you have a bunch of different tenants that are sharing the same database and tables. So each row belongs to a particular tenant, and only that tenant is able to read and write their data. But this means for every tenant, there's a huge amount of irrelevant data that each query needs to sift through to find the rows that that tenant has access to. And if we get rid of this nonsense part of our query and then whack an explain analyze before it so we can see how long it takes to run, and it's probably going to be running for a while. So if we edit that bit out, we can see it took about 17 seconds to return us all of the people that work at Amazon. Now we could speed this up significantly using indexes, and I've got a video at the end of this one if you want to give that a go. But once your indexes are growing out of control, we need to look at breaking up that table. And it's actually pretty simple. Let's create a new query where we're going to create a new table called users. So users is going to be our new partitioned table where we're going to break up each of our users based on their employer. But we want to keep that people table around so that we can do some benchmarking. Now, there are a whole bunch of quite complex tricks for how you can avoid all this duplication of data and make sure there's zero downtime while partitioning your table. So let us know in the comments if that's an example you want to see. But for now, we just want to create a new table for our users. This is going to have the same columns as the people table. But the important part is that we want to partition this table by a list of values in the employer column. So there are a few different ways that you can partition your table. You can do it based on ranges of values. So like in the earlier example, you could have all sales in 2024, all sales in 2023, and so on. You can partition by hash, which is used if you don't have clear separation of basically isolated collections of data within the same table. But we're going to use list, which means we want to partition based on a list of values, which is going to be each of our Mangoes companies. Can't say that with a straight face. So if we run this statement, it's going to create a table that knows it's going to be broken up into a collection of employers. So we just need to create a partition for each employer, which we can do by creating a table and giving it a unique name. So let's say users underscore Microsoft, which is a partition of the users table for values that are in this list, which is just going to be the string Microsoft. So we can highlight just this one statement to run it in isolation and create our new Microsoft partition. We then want one for Amazon, Nvidia, Google, OpenAI, and Supabase. And lastly, we just need to insert the actual data from the people table. So we can insert into the users table, and then we need to specify a list of all of those columns. Thankfully, I've got that in my clipboard. And then to populate the values, we can use a select statement to select those same columns from the people table. And if we highlight over just this one statement and run it in isolation, it might take a while, but now we have all of our users nicely partitioned by their employer. So how do we query this partition table? Well, because Postgres is awesome, we can treat it just like any other table in our database. So we can select all of the columns from the users table where the employer equals Amazon. And if we run this query, we get back just those users who work at Amazon. So we don't need to do anything special to our query just because this is a partitioned table. We can send select, insert, update, or delete statements, and everything just works. In fact, if we delete an entire partition, we get some huge performance benefits, but maybe we'll save that for another video. So in terms of performance, how does our partitioned users table stack up to our unpartitioned people table? Well, let's use our trusty friend, explain, analyze, and see how long this query actually takes to run. So when we select all of our users who work at Amazon, we can see it took about 3.5 seconds. And if we compare that to the same query, but coming from the people table, and we'll highlight just this statement to run it in isolation, and we're back to that number we had earlier of 17 seconds. So a huge performance win there. We're down from 17 seconds to about 3.5 seconds. But what if we want to take it further? Well, since we know that we're only looking for those Amazon employees, we can get rid of this where clause and query a specific partition directly. And if we run this one, we'll see it didn't even take a second. And just to put this in perspective, this query is returning 2 million rows, and the planning time is almost instantaneous because we've told Postgres exactly where to go to get that data. So what happens when we want to insert new data that doesn't fit one of these predetermined partitions? That's a really great question, Jon. Well, let's insert into the users table. And again, we need to specify each of those columns. And then we can use our select trick again to select all of those same columns from the same table, why not, where the ID is equal to 1. So essentially we're just duplicating the first row in this table, but then we want to change this employer to Netflix. I'm afraid that's not one of our special Mangoes companies. So when we run this statement to create our new Netflix user, we can see it fails because there's no partition key for the employer Netflix. So there are a few ways we can manage these partitions as values in that employer column get added. We could do it manually by creating a new table partition for users Netflix for that new value Netflix. But this requires us to know ahead of time every possible value that's going to be inserted into that employer column. Another option is to create a default partition, and then rather than specifying any values, we use the keyword default. So this will work as a catch-all for any employers that don't match our other partitions. And now if we insert our Netflix user, we can see everything's all good. And if we write a select statement to get all of the columns from the users underscore default partition, and we run this one in isolation, we can see this will happily store any of those additional employers that aren't lucky enough to match our special Mangoes companies. But again, this requires us to manually check this partition for common values and stay on top of breaking these out into their own partitions as the size of this default partition grows. What about an automated solution? Well, that's exactly what this PG Partman extension does. As the name suggests, it's a partition management extension for Postgres, and if we scroll down a little bit, we can see it automatically adds new children or partitions for those new values, and can also automate dropping old ones based on retention policies. Okay, we get it. Partitions are cool and they're easy to manage and all of that stuff. But what if we have a situation where we need to query across partitions? Well, let's test it out by selecting all of the columns from just the users table where the is underscore active column is set to true. And let's add our trusty explain analyze so we can see how long this one takes. And I'm assuming it's going to take a while because it'll have to look through every partition to find all of the active users. And that's exactly what's happened here. We've looked through every single partition, but it's actually only taken about 7.5 seconds. What if we do this on the people table? And again, let's highlight this one to run it in isolation. And we can see we're back to that super reliable number of about 17 seconds. So queries definitely perform best if they don't need to jump around between all of those different partitions. But that's still more performant than having all of those rows in one giant table. It might need to scan a bunch of different partitions, but it can do that in parallel over a bunch of smaller datasets. So what else can we do to improve the performance of our queries? Well, you can combine this with other performance optimizing techniques like indexing. But for that one, you need to check out this video right here. We look at how a simple index can massively improve the efficiency of your queries. There's actually a whole series, so why don't you check out this playlist to learn more about Postgres. But until next time, keep building cool stuff.